Okay, so welcome to the last, but not least, session of the conference. Our penultimate speaker is Pieter, and he's talking about hyperfiniteness for groups, actions on trees.
Right, thank you very much, Ilias, for the introduction, and Ilias and Brad for the invitation, and everyone for being here, and for the many people who have already given very nice talks. It was great to be a part of this conference. And so today I indeed want to talk about the title that Ilias just read to you, which is also, a logic connection, a slightly different one maybe than most of the talks that we have had so far. And also, I'm not going to talk really about operator algebras today, but really two things that are maybe related to operator algebras, namely some geometric group theory and some hyperfiniteness in the Borel, a bit also in the measurable setting, so some descriptive set theory as well. And I think this is hopefully still of interest to many people. I think as operator algebraists, we're certainly interested in groups acting on all kinds of things, and then the things you can do with them. And so let me just start with stating the question that I want to answer today, and then later I will also define everything that appears in the question for people who don't necessarily know what all of it means. But so basically the question that I want to consider is the following. Given a group action, G, on a tree T, I'll make this precise, all of this later, when is the action of G induced on the boundary of T hyperfinite? Right, so for people who already know what all these symbols mean, I think the question hopefully makes sense. But I will introduce what everything means if you don't know this question yet. And hopefully I'll also motivate you throughout the talk of why this is an interesting question to look at. But so before I introduce a few definitions, here are two bits of notation. So when I write X or Y or so on, these will be standard Borel spaces. So think, for instance, just unit interval with Borel sets or something like that. And E will denote a countable Borel equivalence relation. Borel equivalence relation on X. And obviously I do not want to keep writing this, so this will be abbreviated to CBER on X. So here Borel means E as a subset of X squared is Borel, and countable means that E classes are countable. Let's break this up, are countable. And so one example is if you have a countable discrete group acting on X, then the orbit equivalence relation will be, if the action is Borel, then the orbit equivalence relation will be of this type, and it's not too hard to show. It's a result of Feldman-Amor that the converse is also true. Whenever you have a countable Borel equivalence relation, you can find a group that generates it as its orbit equivalence relation. So that is certainly a good example to keep in mind. So let me start with defining this last word in the question, hyperfiniteness. So maybe I'll take the next board here. So definition, E is hyperfinite, or maybe let's say Borel hyperfinite. If I can write it as an increasing union of finite equivalence relations. So if E is the union over n and n, say, of En, of an increasing sequence, and this is important because without the word increasing, it doesn't give you anything. Sequence E1 inside E2 and so on of finite Borel equivalence relations. So where finite, that's an extra I, finite replaces countable in the sense that all the En classes are finite. Okay. And this is a notion that has already been studied for a long time. It's very much related to amenability. And in the operator algebra setting, for instance, if you don't think about Borel hyperfiniteness, but in the measurable setting, say you put a probability measure on your space. If you only ask this on a co-null set, this is exactly amenability in the von Neumann algebra framework in a sense. If you have an amenable group acting, it will always be hyperfinite in that sense. And in fact, it's open if any amenable group action generates a Borel hyperfinite equivalence relation. Okay, but so they, in operator algebras, especially the measure version, as well as the Borel version and Borel combinatorics, have seen a lot of applications. So this is something that we generally want to know. Let me maybe first give a few very easy examples. The first example is the equivalence relation E0 on 2 to the n, sequences of zeros and ones, of eventual equality. So where x is related to y, if and only if eventually they're equal. So there exists some capital N, so that from that point on, xn is equal to yn. Right? And by definition, you can write this as such an increasing union, where it's just where at en is the sequences are equal up to after point n. Right? So basically it's immediate. It's that this is the case. A slightly less trivial example is the tail equivalence on 2 to the n, also denoted et. So this is the equivalence relation, and this is one that we will encounter later again, where x is related to y, also if their tails are equal, but now it doesn't need to be necessarily in the same spot. So what I'm really saying here is you can cut off the first n elements of both x and y, and they're the same. Here I'm not requiring that what you cut off is the same length. So in this case, let's say, so there exists n and m, such that for all k, xn plus k is equal to ym plus k. Right, and this is also called tail equivalence for obvious reasons. And the fact that this is hyperfinite is in a paper by Dougherty, Jackson, and Kechris from '94. Essentially, what they do is they reduce the problem of hyperfiniteness here to the one here, where we already know that it's hyperfinite, by looking for every n at the lexicographically least n segment that appears infinitely often in X. If X and Y are tail equivalent, then these segments coincide. And then you put them together in a smart way to basically get elements that are E0 equivalent and reduce the problem from here to here. Roughly, that's how it goes.
This is not the tail equivalence combined with it's not pure
Yes.
tail equivalence.
Sorry, it is not?
Well, I thought pure tail equivalence would be when n is equal to n.
Oh, so that this one is tail equivalence in that case.
All right.
Yeah. Yeah, I know, but yeah, these are the definitions in any case. This one, I think, is usually among descriptive set theories called tail equivalence, but that's just a taste, I guess. Yeah. Yeah, that's allowed. Yeah. But also, it's one can, for instance, prove that any action of z generates a Borel hyperfinite equivalence relation, and by now it's also known for larger classes of amenable groups. But today I'm mostly interested in actions of non-amenable groups. So the question up there is mostly going to be a question for non-amenable groups, acting on things like their Cayley graph or free groups or Batzer trees and so on. So let me also first give you one other definition, because we will need it both to define the boundary of the tree, and also we will use it in the proof of hyperfiniteness of whatever is going to come. So the one other definition from descriptive set theory that I want to make is that of a smooth equivalence relation. So E is called smooth. Sometimes it's also called concretely classifiable. So maybe I should say here definition / theorem. If one of the following equivalence things hold, so one of the following equivalence holds. So the fact that they're equivalent is the theorem part. One is that the quotient space, where I just quotient out by the equivalence relation E, is actually, again, a standard Borel space with the quotient structure. Okay, so this is very nice, right? These are equivalence relations that behave very nicely. The second one, because I'm working with countable equivalence relations, you can show that this is also equivalent to the fact that there is a Borel transversal. So E has a Borel transversal. What does it mean? So a transversal is a set A in X Borel, which is very important, that meets every E class exactly once. In other words, there is a Borel way of picking one element from each equivalence class. And so such that A meets, bring this up a little bit, every E class exactly once. Okay, and so one of the things we're going to do later is go back and forth between these to play around with some smooth equivalence relations. And the smooth equivalence relations are like at the bottom of the hierarchy that I'm going to mention in a second. They're very nice and very understandable. We basically know everything about them. And so I guess I lied when I said it was only two definitions. There's one more definition from descriptive set theory that I want to make, and it's the of Borel reducibility. So within the world of Borel equivalence relation, there's a nice way of comparing the complexity of equivalence relations to each other. And so we say that, but this I just mean E equivalence relation on X is Borel reducible. To some other equivalence relation f, say, on y, if the following holds, there exists a function f from x to y, Borel as usual, such that x is E related to x prime if and only if f of x is f related to f of x prime. Right. In other words, through f, you can view E inside of f, essentially. Okay. And really, the way to think about this is that this means that E is easier than f. If you know how f behaves, then you just put E in there and you know how E behaves. Okay. So E is somehow easier than f. Okay. And so here are some facts. Oops. So this, we can also say things about smoothness and hyperfiniteness with respect to Borel reducibility. And we will use some of these. So the first one, I'm just going to state it, but even though I'm not going to use it, E is smooth if and only if E Borel reduces to just the equality relation on whichever Polish space you like. Right, so it reduces to something that is very easy to understand. And the Borel reduction is just using the second one or the first one. You can either, the first one is the easiest. If X mod E is Borel, then the quotient map gives you this Borel reduction. The second one is slightly less trivial. Namely, if f is hyperfinite, and E Borel reduces to f, then E is also hyperfinite. I think this was first observed in a paper by Jackson, Cashrus, Louveau in the 90s. I don't remember.
Your definition, that's not true, right? Because you don't find it in a translation.
Sorry?
Oh, sorry, yeah, yes, thank you.
So, with your definition, I mean, you won't find it by translations.
Mm-hmm.
So if E reduces to F, I mean, it could be at continuum many things are going to the same point. So you want to say something else, I guess.
No, because these are countable equivalence relations, right?
Well, if F is countable and also you assume they're countable.
I'm assuming all my equivalence
oh.
relations are countable. Yeah. If my equivalence relations are not countable, this is definitely not true.
Sure, okay.
But if my equivalence relations are countable, then automatically such a map has to be countable to one at worst. Yeah. Thanks for pointing that out, though. Yeah, but so maybe I should have specified that more. But yeah, I'm assuming that every equivalence relation in this talk is countable. Yeah. And if it's countable, then it's actually not too hard to prove, and you can either look it up or try it as an exercise. It's not that difficult. And the last fact that I'm going to use is, well, once you have Borel reducibility, this is obviously a pre-order. I can also define equivalence in this sense, which is called Borel bireducibility, namely E reduces to F and F reduces to E. This also has a nice characterization. So E is Borel bireducible with F, right? And just with that, I mean E reduces to F and F reduces to E, if and only if there exists a bijection between the quotient spaces, just set theoretically, right? If my equivalence relations are not smooth, then these are not Borel spaces, standard Borel spaces, but just a bijection, but that lifts to a Borel map from X to Y. Okay, so this is one other way of looking at Borel bireducibility. Okay, so the things on this side are tools that we're going to use to show that the actions that I will introduce next are Borel hyperfinite. Okay, so unless there's any questions about this part, I'm now gonna, yes. Yeah. So this will, certainly for countable Borel equivalence relations, like this indeed looks asymmetric, but if you have such an F, you can also find one in the other direction. Not always, I think, no. Yes, David.
Does smooth imply hyperfinite, or does hyperfinite imply smooth?
Smooth implies hyperfinite, but not the other way around, right? Because if you look, for instance, right, if he is smooth, I mean, in any of the three characterizations that are on the board that is smooth, it's not too hard to show that they're hyperfinite. Certainly the one on top and the Borel transversal one. E0 is hyperfinite, but not smooth. That's an exercise if you want. And yeah, generally, I mean, the hyperfinite equivalence relations that we're going to get to, they're not going to be smooth. The smooth ones are somehow the trivial ones, like these we don't really care about too much.
So for the proof of this last one is that's the same as the proof of the Cantor-Byrne thing.
It's similar, yeah. You just do something, yeah.
Will the maps not automatically preserve from the equivalence? I mean, if you look at the Cantor-Byrne thing construction going back and forth, it seems to me that that's going to be Borel and also compatible with the equivalence rules.
Yeah, I think so, right?
Okay.
But it's more complicated because your F, I mean, it's not functions are not injections. So if you lift it to a Borel function, the Borel function is not injection.
Yeah.
And if you're working with these quotient spaces, then you're in funny.
I mean,
you're not with standard spaces. So it's more subtle than that.
It's certainly not exact.
That's just Hannes's question. I mean, there is for example, you can just have a smooth and also smooth, but you just double the points. So they are the same equivalent, but you don't get the bijection.
Yeah.
Suppose you look at the vacuous equivalence relations where it's just sets 1 point orbits.
But then there's nothing, right? Because we already are assuming that this is a bijection, right? And then.
I'm thinking going to the top of one.
Oh, when they're both Borel bireducible? Yeah, then you're doing Cantor-Bernstein. But in general, these, like, as Elias was saying, in general, this Borel map does not need to be injective at all. And we will in fact see an example of that in a few minutes.
Yeah, but the Cantor-Bernstein also seems to be injective. So this is more general.
This is certainly different, more general. Yeah, this is more subtle and more general than Cantor-Bernstein. Yeah. Oh, yeah. Okay. So next I want to explain what these actions are, what I mean with these trees and these boundaries, and what exactly the objects are that we want to study these set theoretic things for. So actions on trees. So T will be a countable tree. So just a non-directed graph without loops that is countable. I'm not assuming it's locally finite. A vertex could have countably many edges. Here is an easy example that we all know, right? The Cayley graph of F2. I will in fact come back to this one. So let's just draw it. Right, this is an example of a countable tree. Keep doing this. And so in T, so here are some definitions. The geodesic ray, this is the main thing we're going to be looking at, is an infinite injective path, basically one-sided, so sequence or infinite injective sequence of subsequently adjacent vertices. Right, so you choose a vertex to start, and then you just start wandering off. You're not allowed to backtrack. So really what it means, you start at some vertex, say this one, and then you start running off to infinity in some way. Right? These are the geodesic rays, just infinite paths in my space. And let's introduce a notation for them. So with geo of T, I will mean all the geodesic rays. Right, and so this will be a subset of vertices of T to the power n. I just look at them this way. And first of all, we have a very canonical action, monoid action of the natural numbers on this. By just forgetting the first vertex. Okay, so I have an action here where one acts on V0, V1, V2, and so on, by just forgetting the first vertex. Okay. And the reason is that, right, the boundary, for people who've heard of it, right, it's geodesics that are eventually equal, right? Which means that they will be in the same equivalence relations generated by this action. Right? This is really similar to the tail equivalence from before. And so by definition, right, the boundary of T will just be the quotient space of this for this action of n. Right? This is not a group action, right? But this is some countable to one function. Right? What I mean with this is 2 points are related if I can find m and n that send the x and y to the same thing. Right? In this case, it will mean that, after cutting off finitely many vertices of each, possibly different length, you get the same geodesic. And this is the Gromov boundary. Right, so that's the definition of the boundary. I mean, a first thing that one can ask if you haven't seen this before is, well, this is just a quotient by some equivalence relation, right? Is this even in the standard Borel space? And there's different ways of seeing that, but for instance, with the things I have written before, it is very easy to see that this is standard Borel space. I mean, if you assume that because the equivalence relation will be smooth. Right? The equivalence relation that this action generates is smooth because a Borel transversal is pick your favorite vertex, and the Borel transversal is all the geodesic rays starting at that vertex. Okay, so that gives you a very nice Borel transversal, and so this will be a standard Borel space. Right, so with here, maybe I should write like the equivalence relation generated by n. So note delta t is standard Borel. So that is good. And another observation that we can make is if I have an automorphism of the tree, right, and I can make it act on geodesics by just acting pointwise, this is going to commute with this action of the natural numbers of forgetting the first vertex. And so because these actions commute, any automorphism of T induces an automorphism on the boundary. And so this group acts on the boundary. So out of T, let's say commutes acting on GOT, commutes with this action of N that I just defined.
Can you just go back to this standard Borel? I'm missing something. You can only count only many vertices, right?
Yes.
And there are continuum many different elements of the boundary.
Yes.
So how can you use vertices and invariants? You said that you just pick a vertex.
Oh yeah, no, I pick a vertex and then the Borel transversal is all the geodesics starting at that vertex. Right, I'm working on the space of geodesics, right, of geodesic rays. There's uncountably many geodesic rays, right?
Right, but from any vertex, there are many.
And from any fixed vertex, there's uncountably many rays starting there. But I'm saying this is a Borel transversal, right? If you have two different geodesic rays starting at the same vertex, they're different, right? They're not equivalent in this equivalence relation.
So invariant is ray with the vertex.
Yes. Yeah.
Yes.
Yes. Yeah. But you fix one vertex basically. Yeah. So every vertex gives you a different Borel transversal of this equivalence relation. Yeah. I hope that's clear to everyone. Okay. So yeah, so really, if you want, you can really think of this boundary. If you don't like this equivalence relation approach, you can just think of the boundary as fix your favorite vertex, and the boundary is really just the set, nothing more, nothing less, the set of all geodesic rays starting at that vertex. So that's one other nice way of just thinking about the boundary without having to really have all these equivalence relations in your mind. But here, because it's obvious that automorphisms of T commute with that, whenever I have a group that acts on the tree by automorphisms, I have an induced action of the group on the boundary. So if G acts on T, then I have a natural induced action of G on the boundary of T. And so now I think by now, right, the question that I said earlier hopefully makes sense, right? So if I have a group acting on a tree, so G is also always a countable group for me. So when is this induced action hyperfinite? So this is the question that I want to consider in the next 20-25 minutes of the talk. All right, so some things, I mean, this question is in fact relatively old. Here are some, I'm going to remain a little bit vague, but here are some examples. The first example is one that I erased by now. If you look at the free group on two generators, so for me the bold face F is the free group, and you like that act on the boundary of its own Cayley graph for the standard free set of generators, right? That graph over there. This is basically tail equivalence, right? Because if I act with an element, it means that I just put some initial segment there. And so two things are equal if up to initial segments they're the same. So this is essentially tail equivalence. And so it follows from Dougherty, Jackson, Cashwis, that for this tree and for this action on the boundary of the tree, you get something hyperfinite. Okay. And so because I want to get to the main theorem that I have with my co-authors, and I guess I didn't mention them in the beginning. So up to now, I mean, this is all background, but the theorem I will mention later is joint work with Sri, Koichi Oyakawa, and Forte Shinko. But so let me mention maybe in this way. So This is also known for certain actions in some of them, many actions in others. So certain actions of groups that are very similar to the free group in the sense that they're all some version of hyperbolic groups. So this is known for actions of hyperbolic groups. So maybe I should include some references. I'm not going to write all the names. You can ask me afterwards. So Huang, Szabok, and Shinko did part of this in 2020. Then Marquise and Szabok continued on that later in 2020. And Narishkin and Andrea have some more recent approach, also using something called Borel asymptotic dimension in a recent paper from this year. Oops. Oops, there goes the chalk. Oh, maybe I should not erase this yet. Actually, yeah. Sorry, let me come erase something here. And then you can, there are generalizations of this in various ways. So again, certain actions of, so let me continue somewhat here, hyperbolic groups, also mapping class groups have been considered. So this was in a paper by Pieter and Szabok, 2021. Then one of the papers that was a motivation for what we did is for relatively hyperbolic groups. This was Karpinski last year. And also one of my co-authors, Koichi Oyakawa, has some results for accidentally hyperbolic groups from just this summer. So all of these somehow use these geometric conditions on the groups that are hyperbolic or one of these, and construct and use properties that actions of such groups have to kind of like really construct in a really constructive way, show that the actions are hyperfinite on the boundary. And so the main thing that we did was realize that there's actually a very natural condition, just in general, without many like restrictions on the group, that basically incorporates most of the results that are known here and gives you a very direct way to see why these equivalence relations are hyperfinite. And so that is the main theorem that I want to prove today. So this is earlier this summer with the co-authors that I listed over there. And so here is the assumption. So if you have a group, any group acting on any countable tree, with the following conditions, so such that every geodesic ray say I call it V, has some initial finite segment, has an initial segment, so some finite geodesic, I'm gonna write it with this. So with this, I just mean that sigma is the first finitely many for some finite number of V, some initial segment, so that the stabilizer of the whole geodesic ray coincides with the stabilizer of just this initial segment, such that the stabilizer of sigma is equal to the stabilizer of V. Then the induced action on the boundary is hyperfinite. So then the action of G on the boundary is Borel hyperfinite. Okay. And if you go through these papers that I mentioned of results that were known before, you will see that in fact most of the actions that appear in those papers actually do satisfy this condition. And we also get a little bit more, some examples that were not covered yet. And so let me just briefly point out that, for instance, yes, Andrea.
Maybe something that many of the Pieter interventions, they involve actions which are not on tree, they're on tree grass.
True. Thanks for pointing that out. I should have said that. So we specify two actions on trees. When there is more restrictions on the groups in many of these papers, they have actions on graphs that are not necessarily trees. On K, they're often like somehow like have like, yeah, the Cayley graph will certainly never be a tree except when you're a free group. So thank you for pointing that out. Yeah, we restrict to actions on trees. So we remove many restrictions on the group and the action, but we do ask that we're acting on a tree. Whereas indeed, it is true that for many of the examples that I mentioned, they also involve actions that are not necessarily on trees. Thank you.
I just want to say we have no assumption on the group at all.
Yeah, exactly. So the main generalization for us is that we have zero assumptions on the group. But we do have assumptions on the graph, namely that it is a tree. Yeah. And so here are at least two, I mean, in my opinion, nice examples to which this applies. So this applies to any acylindrical action. Cylindrical actions. I'm not going to define what these are. This is a very well-studied notion in geometric group theory. And for instance, many actions of hyperbolic groups and so on will be acylindrical, but you can have acylindrical actions of many things. And the reason that these are examples is if you look at the definition of acylindrical, it's easy, basically immediate to see that stabilizers of these finite segments are finite groups. And so once you have a finite segment with finite stabilizer, because the stabilizer of the whole geodesic ray is just the intersection over all the initial segments increasingly, when you're finite, like at some point they have to become the same. So once you have that stabilizers of long enough finite segments are always finite groups, then you get this condition. And maybe a more concrete example, if you take an amalgamated free product of two groups over some common subgroup, and you let it act on its Bassera tree. When, and here, this K is what is called almost malnormal, so it's not too much of a normal group. Meaning that if I look at K intersected with one of its conjugates, this is finite. So yes, David. Sorry, say again.
Do you assume that condition for K as a subgroup of V?
K as a subgroup of the amalgamated free product. Yeah.
Are there conditions under which you could just if you assume something about how it's inside of P and how it's inside of H, then does that imply that there's some easy to check condition without having to know?
I mean, I think if this is true in both G and H, then you're fine, for instance. Yeah. Sorry?
I've never seen malnormal. I mean, I've seen malnourished.
Well, I don't know. There's so many different versions of saying that the group is not very normal. This one is called almost malnormal. Because this means that K is not very normal at all, right? Because if you conjugate it, it's somehow very far from itself, right? Because the intersection is only finite. No, finite. So the intersection of G with its conjugate is finite. So K is busy, like being sent around a lot. Yeah. Maybe K is also malnourished. I don't know. The reason is, so the Bassera tree is, let me just quickly define it in words. If you haven't seen it, don't worry too much. So this is a group with vertices, the cosets of G and H in this amalgamated free product, where you put an edge between a coset of G and a coset of H if it's a coset of the same element of the big group. This is a locally countable tree. And you can show that the stabilizers of finite geodesic segments are just, or of edges, and therefore also segments, are conjugates of K. And so this condition will imply that those stabilizers are finite. And you get this theorem. There's two reasons that I'm including this. I mean, it's a concrete example, but also this was kind of a motivating example for us. We first worked through this case, and then realized that we can, that really the stabilizer condition was the one thing that we needed. Okay, so I realize I've been a bit slower than I expected, but let me try in the next 10-15 minutes to just prove this theorem, because one of the good things of what we realized, it's the paper is a relatively short note. Basically, once we realized that this was the correct framework, the proofs becomes very short and very easy. And I should be able to give it to you in the next, say, less than 15 minutes. So here are two very easy lemmas. Lemma 1, let's make sure I keep my own notation. So if you have actions m times n on Borel space X, so here m and n, you can think of them as groups if you want. We will use it also for this action of n. So in general, these are just going to be monoid actions. So when they're monoids, I have to assume something, namely that they're countable to 1, just like the actions from n that we saw earlier. And if one of them, so if I look at just the action of n, if this one is smooth, then I have the following equivalence. So if I look at the equivalence relation generated by m times n, this is Borel bireducible with the equivalence relation of just the action of m on the quotient space of n, right? And the fact that n is smooth makes this well-defined, and they commute. So m induces an action on here. And if you remember earlier, Borel bireducibility just meant having a bijection here that lives to a Borel map. If you just look at the Borel map from X to this quotient space, which is the canonical quotient map, it's immediate that this just descends to a bijection between these quotient spaces. So that's the proof. So that's one lemma. The second lemma is almost as easy. If I have some equivalence relation, so if E is a countable Borel equivalence relation on X, and I have X written as a union of some Borel subsets AN, such that E restricted to AN is smooth for all n, well, then also E is smooth on X. So then E is smooth. The way you do it is, these are all Borel sets. First, you make sure that this is a partition. Each of these partitions has a Borel transversal, and the union of those is a Borel transversal for the whole thing, so done.
Are those sets in area?
No.
So you make sure to remove something from transversal. But okay, you can.
Yeah. I mean, yeah, you have to adjust the sets a little bit to make sure, but essentially you're just unioning up to like one or two one-line subtleties. You're essentially just taking the union of Borel transversals, and it works, I promise. So these are two very easy observations about countable Borel equivalence relations. And the last ingredient, and let me now state it in its full glory. So this theorem of Dougherty, Jackson, and Kekjes that I have already referred to, that implies that the tail equivalence with different lengths of tails is hyperfinite. It tells you if you have an action of the natural numbers that is countable to 1, then it generates a hyperfinite equivalence relation. Is hyperfinite. And the proof is exactly the one that I, in words, gave you earlier for tail equivalence. Because this really means that your equivalence relation is just generated by one function, and you do the same trick. So this is one of the fundamental results in their paper. Yes. The M and N are monoids. Yep. But we will only use it for groups and the natural numbers. So if you want to just restrict your attention to those, that's fine. And even only for the action of the natural numbers that I just erased. Okay, so here's the proof of the main theorem. There is a theorem. Okay, so first of all, we're going to break up our space into pieces that we can handle well at the beginning and use lemma 2. So let's make one definition. So for any finite geodesic sigma, we define the following space, a subset of geodesic rays, namely just the geodesic rays that start with sigma, but additionally, so this is all V in geodesic rays, such that they start with sigma, so I'll write it this way, and they have the same stabilizer. So the stabilizer of sigma is equal to the stabilizer of V. So it's all geodesic rays extending sigma that have the same stabilizer. Right? Some of these may be empty, but the condition that we have over there guarantees that the union of these over all sigma gives you all geodesic rays, because for all geodesic rays you can at least find at least one. Right? So that's the first observation. So geo of T is the union over all sigma of these geosigmas. The second easy observation is that these sets are closed. So geo sigma T is closed, and therefore Borel, right? I just want Borel sets so that it makes sense when I restrict my equivalence relation. And so now that I know they are Borel, we can look at, okay, what is the equivalence relation, right? So maybe let's call the equivalence relation generated by this action E, or maybe I should call it, I should be more precise. So E G delta T. Oh, sorry, that's the one I want to get to. G acts on T, so G also acts on geodesic rays. That's the first thing I want. So if I look at the equivalence relation of G acting on rays, and I restrict it to one of these Borel sets, geosigma, right? What is happening? Well, what does it mean that I take the equivalence relation restricted to this, right? So I'm only looking at things that start with sigma. So I'm only looking at other geodesic rays for which G leaves the initial segment sigma invariant. So it's really the equivalence relation generated on this set, generated by the action of the stabilizer of sigma. Right? So this is E of the stabilizer of sigma acting on geosigma. Because I restrict to this, I'm assuming that sigma remains where it is. But by assumption, right, the stabilizer of sigma, right, is equal to the stabilizer of V for any V in this set. So this is just a trivial action. So it's certainly smooth. Right, so this is trivial, hence smooth. Okay, and so now I just apply the lemmas and the theorem from this board. Let me maybe erase this part. Right, first of all, I have these smooth equivalence relations restricted to these subsets. I union over all of them using lemma, which was the lemma with the union, lemma 2. This tells me that the action of G on the geodesics is smooth. All right, but so, oh, wait, I should write something here, is smooth. Okay, but now we're in the, we can have a look at this theorem, right? If this action is smooth, then it means that the quotient space is standard Borel. But again, as observed before, this action of G commutes with the action of N that we introduced earlier. So now I have an action of N on this space, right? an action on n on a standard Borel space, which is countable to 1 in our case, so it generates a hyperfinite equivalence relation. Right, so this is theorem, maybe I should also give it a number. So theorem 3. So theorem 3 tells me that the equivalence relation on this space generated by n is hyperfinite. Okay. And now you can maybe see what is going to happen, right? I still haven't used lemma 1. I want to go from this to this, right? But the boundary of T is just a quotient space of T by n. So really what I have to do is swap these. And if I just apply lemma 1 twice, that's exactly what is going to happen, because this is these actions commute, right? So, but let me spell it out. What lemma 1 now tells you, because both the action of n and the action of g are smooth, so the smoothness I can use for both m and n in that theorem. So it tells me that the one that I'm interested in, the action of g on the boundary, which, remember by definition, the boundary is just the quotient space for n. This is Borel bireducible with the action of g times n on geodesics. And then I use lemma 1 again. Now here I use the fact that the action of n is smooth. Now I'm going to use that the action of g is smooth. This is the same as the action of n on this quotient space. And this is hyperfinite. I told you earlier that hyperfiniteness doesn't change under Borel reductions, so certainly not in the Borel bireductions. So that shows it to you. Okay. So this is a very short elementary proof, I would say, that once we realized that this was the correct condition, everything just falls out nicely. And maybe in the last 2 minutes, let me maybe say a word without writing anything about 2 other things. So for one, we can also get measure hyperfiniteness under some slightly weaker conditions here. I certainly do not have time and also do not want to introduce all the definitions, but if in this theorem we replace that these stabilizers are actually equal by the fact that the stabilizer of V is so-called uniformly co-amenable in stabilizer of sigma, really think of it as a condition to say that the stabilizer of V is not too much smaller than the stabilizer of sigma. Then with roughly the same idea of proof, we can show that the equivalence relation on the boundary is measure hyperfinite, meaning for every Borel measure that I put on the boundary, I can find a conal set and the restriction to which is hyperfinite. And the thing that is going to happen here is in the definition of geosigma, we're just going to replace also this condition by being co-amenable. We prove that this implies that the action here is not going to be trivial, but it's going to be Borel amenable. And then we run through this whole proof and use this notion of Borel amenability, which I also haven't introduced, to conclude measure hyperfiniteness. So that is a very nice measure version under weaker conditions. And the last question that I want to mention is, well, if you see all of this, right, you may wonder, can you give me an action of a non-amenable group, say, on a tree, so that the induced action on the boundary is not measure hyperfinite or not Borel hyperfinite? We actually asked this question to several people in descriptive, or a few people in descriptive set theory, and most of them said, I don't know. But it turns out that this is known. And in fact, Alekos Kechris already did this in 2005, if I remember correctly. He introduced, he showed that the so-called modular actions, whatever these are introduced by Jort, give you such examples. So in fact, the statement becomes that any residually finite group has an action on a tree, so that the induced action on the boundary is free and preserves a probability measure. And this immediately tells you that when you have a non-amenable residually finite group, that action is not going to be measure hyperfinite. And for instance, this works for free groups. And for free groups, you can in fact try to write down somewhat concretely what this action is. But in general, the question certainly remains, which actions are hyperfinite, which ones aren't? Here I showed you one kind of nice, I think, natural conditions where they are. there are examples where they are, and there's also many examples where we have no idea. So that's all I wanted to say. Thank you very much.